This learning module covers Section 1.3, Astronomers Use Mathematics to Find Patterns. The topics covered include finding patterns, reading graphs, recording measurements, and using units and scientific notation. We start with an overview. The learning goals are to understand how measured data values are recorded and plotted, and be able to extract meaning from a graph.
This lecture discusses the material in Section 1.3 of the textbook, Astronomers Use Mathematics to Find Patterns, Reading Graphs. Science is a systematic study of the structure and behavior of the physical and natural world through observation and experiment. Through this process, patterns and rhythms in nature are discovered. Most natural phenomena are predictable. Mathematics and science work together because mathematics works when it is used to describe nature and the patterns we see. We are confident that if we do the job right, our predictions will be correct. Plots, graphs, and charts are ways to visualize data. There are many kinds of charts that you're probably familiar with from using Excel and other spreadsheet packages. In this lecture, line graphs and scatter plots are discussed. When you see a new graph, study these 4 things. What is plotted on the horizontal axis? What is plotted on the vertical axis? What is the trend of the data? Is it up, down, or flat? And how fast is it changing? The learning goal for this lecture is to be able to read line plots and scatter plots and work with functions of distance, velocity, and acceleration. Line graphs are used when one variable, the independent variable, affects another, which is the dependent variable. They are useful for predicting trends. The title of the plot is Inverse Square Law Experiment. The subtitle indicates that this is measured data using a 100-watt light bulb and measuring its brightness at increasing distances from the bulb. 4 questions are first answered before interpreting the plot. What is plotted on the horizontal axis? Read the blue label. The horizontal axis is distance from the bulb. The values are given in units of meters. The range of the data is from 0 to 0.2 meters. That's 0 to 20 centimeters. What is plotted on the vertical axis? Read the red label. The vertical axis is brightness at distance. The values are given in watts per square meter. The values range from 0 to 20,000 watts per meter squared. What is the trend of the data? Up, down, or flat? The farther you are from the bulb, the fainter it appears. How fast is it changing? Well, it changes rapidly closest to the bulb and slowly farther from the bulb. From the plot, we can read individual values to some level of precision. Here we see that at 5 centimeters from the bulb, the brightness is 5,000 watts per meter squared. In this plot, notice the axis values now on the left are increasing by factors of 10. This is the same data but plotted on a logarithmic scale. Also notice that the axis does not need to start at 0. Scatter plots are similar to line graphs. One use of a scatter plot is to show how much one variable is affected by another. The relationship between 2 variables is called their correlation. Sometimes the data points in a scatter plot form distinct groups. These groups are called clusters. Clusters reveal an underlying taxonomy, or classification, of the data. In the scatter plot to the right, we see a correlation, or a trend, between height and weight in humans. Generally, the taller a person is, the heavier they are. We see clusters. So in this cluster plot, we were supposing that we wanted to study the evolution of people through the years, and we decided to go where people were being born, a maternity ward. So we see these clusters. Upon further analysis, we find that the clusters tell us about the stage of life of people. The shortest groupings are the newborns. They were visited by a few older siblings and 2 preteens. Most of the adults were women, and the plot above the main adult clusters are women who are pregnant but haven't given birth yet. Clustering is a useful way to develop a taxonomy or classification system of entities based on some set of observable attributes. Print out the handouts for position, speed, and acceleration, and for your speed due to Earth's rotation. Speed. The speed of anything is the distance divided by time. There's really two speeds we talk about. First is the average speed over some interval of distance divided by some interval of time. We also talk about the instantaneous speed. That's as you shrink the time interval to nearly zero, what is the speed? Today we're only interested in using the average speed. If the position of the car at time 10 seconds is 30 meters and the position of the car at times 20 seconds is 60 meters, then the average is 60 minus 30 meters, traveled 30 meters, in 20 minus 10 seconds, in 10 seconds, or 3 meters per second. The acceleration of the car is the change of the velocity divided by time. Just like the velocity, there's an average acceleration, which is the change in speed over some big time interval, and an instantaneous acceleration, which is the limit in which that time interval becomes very small. Today we're only interested in using average acceleration. If the speed of the car at time 15 seconds is 3 meters per second and the speed of the car at time 25 seconds is 2 meters per second, then the average acceleration is negative 0.1 meters per second squared. Let's work through three special cases: constant position, constant speed, and constant acceleration. Let's start with constant displacement. Displacement is the distance from some reference point. We measure the distance of the parked car and it isn't changing in time. It's always 50 meters away from us. Using the formula for speed, we find that the speed is zero because it is not moving. Likewise, the acceleration is also zero. Let's make a plot of the position, velocity, and acceleration of the constant position case. We see that the position is always 50 meters. It's a flat line. The velocity and the acceleration are always zero. They are also flat lines, zero slope. The mathematical model for this motion is given by these equations. X equals 50 meters, velocity equals 0, and acceleration equals 0. Now let's consider the constant speed case. We measure the position at every 2 seconds and find that the relative displacement is constantly increasing. It is traveling away from us. We measure the position as 10, 50, 90, 130, 170, and 210 meters. The average speed between all of these points is 20 meters per second, and the acceleration therefore is zero because the speed is constant. This is also found from the formula for acceleration and the formula for velocity. What do the constant velocity plots look like? The position is a linear function. The velocity is a constant value, always equal to 20 meters per second. The velocity is the slope of the position plot. It is the rise divided by the run. The acceleration is zero. The mathematical relations are that the position is equal to 10 meters plus the product of 20 meters per second and the time traveled. That's the velocity times the time. The velocity function is a constant value. It's always 20 meters per second, and the acceleration is always zero. Let's look at the constant acceleration case. The position values are measured every 2 seconds and found to be 10, 18.6, 44.4, 87.4, 147.6, and 225 meters, respectively. The speed is the difference in the position divided by the time. For the speed at 1 second, 10 meters is subtracted from 18.6 meters, and the value is divided by 2 seconds. The result is 4.3 meters per second. For the speed at 3 seconds, subtract 18.6 from 44.4 and divide by 2 to get 12.9 meters per second. The acceleration is found by subtracting these two velocities and divided by 2 seconds to get 4.3 meters per second squared, which is about what the Saab 9.5 Hirsch is capable of. Use the formula to find all the values of speed and acceleration. The acceleration always turns out to be 4.3 meters per second squared. This is a constant acceleration case. What do these plots look like? Plotting the values, we see that the position is parabolic, the velocity is linear, and the acceleration is a constant value. The mathematical model is that the position is the sum of the initial displacement plus 20 meters per second times the elapsed time plus 2.5 meters per second squared times the square of the elapsed time. The velocity is a linear function. It is the product of the acceleration and the square of the elapsed time. The acceleration is constant, 4.3 meters per second squared. It might seem like a trivial set of cases, but if you zoom in close on any plot, it looks linear. So these three cases are very useful for showing the behavior of systems in motion. Now let's consider rotational motion. The radius of the Earth is about 6,371 kilometers. The circumference of the equator is 2 pi times the radius. That's 40,030 kilometers. At a latitude above or below the equator, the circumference is smaller by a factor of cosine of the latitude. At the poles it's 0 because the cosine of 90 degrees is 0. One day has 86,400 seconds. Dividing the circumference at the equator by the number of seconds in a day, we find that a position on the surface of the Earth at the equator is traveling 0.463 kilometers per second due to the Earth spinning. This isn't even considering the motion due to the Earth orbiting the Sun. The speed is over 1,000 miles per hour. In summary, astronomers are fascinated by a beauty of the world that includes a mathematical aesthetic. Developing mathematical models of the world is a satisfying and pleasurable activity.